In this video, we're going to talk about equilibrium and how that can be calculated using a tool called ice charts. For almost the entire year, we've looked at reactions that really only go in one direction. If you take magnesium and you burn it, you're going to make magnesium oxide. Could balance this, it would look like this. But overall, the reaction only goes in one direction. It only goes to form magnesium oxide. If you have any leftover magnesium oxide, it doesn't spontaneously go the other direction at our conditions. However, there are reactions that go both directions depending on what things like the temperature or if the concentration changes. So when reactions go in two different directions, you can have the presence of both chemicals and the reaction seems to be done. So when it is at equilibrium, if both elements from the reactant side and the chemicals on the product side, if they're both present, that existing at equilibrium uses this double arrow right in the middle. So it shows us that it can go in both directions. And it doesn't mean that it's done changing. It means that as nitrogen dioxide forms dinitrogen tetroxide, some dinitrogen tetroxide is forming back into nitrogen dioxide. So in order to calculate how much of each chemical is present, we use an equilibrium constant, and then we use these ice charts. The equilibrium constant is represented by the letter K. So KEQ. KEQ represents the equilibrium constant, and it is calculated using both the coefficients of the reaction and the products and the reactants. So this is true for gases or aqueous substances. If we're talking about a liquid or a solid, those do not get included in the KEQ expression. But if your reaction is 1 of letter A plus 2 of letter B exists in equilibrium with 3 letter C's and 4 letter D's. If you have a chemical reaction that looks like this, the equilibrium constant can be calculated by looking at the concentrations or the molar amounts of a gas at equilibrium. So the KEQ is the products divided by the reactants. And when we say that, we mean you take the concentration of chemical C at equilibrium and you raise it to the exponent of the coefficient. And then that is multiplied by the concentration of letter D at equilibrium to its coefficient, to the power of its coefficient. And then on the denominator, we have A to the first power times B to the second power. So whatever the coefficient is in the reaction, that functions as the exponent in the KEQ expression. So, and these variables are representing the concentration at equilibrium. So when the reaction is done changing, what is its concentration? And again, remember, it is only for gases or aqueous substances, not solids or liquids. So in the first example from your in-class work problems, it gives you an expression. It gives you a reaction, and it says at equilibrium, these are the number of moles of the gases. So A, C, and D are the ones that we care about. You can't use B because it is a solid. So we just use the letter 1 in the KEQ expression for B. So for us, the question is, what is the KEQ? So we know that KEQ is C to the first times D to the first over A to the second. And since, again, B is the solid, it would just be times 1. So you don't need to include it in the expression. So at equilibrium, it gives you all of these values. C was 2.30 times 10 to the negative 5th. D was 7.17 times 10 to the negative 4th. All of that is divided by 0.120 of A to the second power. And so if you did this on your calculator, 2.3 times 10 to the negative 5th times 7.17 times 10 to the negative 4th, the product of those two numbers divided by 0.120 squared, you get 1.14520 times 10 to the negative 6th. Since all of these numbers have 3 significant figures, we have to round this number to 1.15 times 10 to the negative 6th. And there are no units for this. All of the concentrations end up canceling out. So the KEQ expression is just the number 1.15 times 10 to the negative 6th. So question 2 is a little bit different than question 1 because it tells you how much you start with and how much you ended with. And it asks for what is the concentration of each gas species in the system at equilibrium. So this is where we're going to begin using the ice chart. If it asks you how does it change, we have to use the ice. So it is 2A plus B yields C plus D. And the I and the C and the E are going to represent parts of the reaction and which stage of the reaction we're talking about. So I stands for initial, C stands for change, and E stands for at equilibrium. What are the concentrations? And this is what is used in the KEQ. The values at equilibrium. So in the question, it says you start with 0.80 moles of A. And that's it. That's all it tells you start with. So we don't really care about B because it is the solid in the system. But if it tells you that the amounts you start with and it only tells you A, that means that these are probably 0. So you can assume that the amounts of the chemicals not listed, if you're given starting values, you have to know that the other ones are 0. We know that if you end with 2.10, 10 times 10 to the negative second moles of D, that we know that the change for C was 2.10 times 10 to the negative second. So this is everything that the problem tells us. It tells us the initial concentration of A, or the initial number of moles, and it tells us the equilibrium number of moles for C. The other things that we can infer based on the reaction are that anytime you have the same molar ratio, you're going to have the same change. So D also should end with 2.10 times 10 to the negative second moles, because for every 1 mole of C that you make, you will also make 1 mole of D. And we know that if C and D increased by 1 mole, then A must have decreased by 1 mole. But in reality, it's not 1 mole. A has to decrease by twice as much. So you can subtract 2.1 10 to the away. 2.1. So at the equilibrium concentration, 0.779. So in this case, we have seen the concentration at the beginning for A and the change for C and D, which produces an equilibrium, and the change in A has to be proportional to the change for C and D. And so when that happens, you can calculate the concentration at each at equilibrium for each species. One quick comment on this: the conditions of this reaction are different. This happens at 250 Kelvin, whereas in the first one, it happens at 100 Kelvin. So the conditions are different, which is going to produce a different KEQ. So this is kind of an important point. Temperature is the only factor that can change a KEQ. So temperature is the only factor that can change a KEQ. So in question 3, we have the same reaction and we have the same temperature that we had in reaction number 1. So now we know the KEQ because we already solved for it. If you don't remember, the KEQ at 100 Kelvin is 1.15 times 10 to the negative 6th for this reaction. So that will always be true for this reaction. Now it gives us the reaction of 2A plus B yields C plus D. And it gives us our initial amounts. So if you start with 2.0 moles of A, the question is, what are the equilibrium concentrations for every gas? So we don't have any final concentrations given in the problem, but we do know that using the KEQ expression, we know that KEQ, so this is at equilibrium, we know that the products divided by the reactants are true. And since we know that we didn't start with any C or D, we only started with 2 moles of A, it's going to increase by some amount, and this is going to increase by the same amount, and this is going to decrease by 2 times that amount. And so in our KEQ expression, we actually can solve for the x values, because 0 plus x is x, and 2 minus 2x is 2 minus 2x. And so at equilibrium, you only have one number now. We have x. X is the only variable that we don't know. So you could take your KEQ and say that C times D is x squared, and 2.0 minus 2x is squared, and all of that equals the KEQ that we identified earlier in the question, 1.15 times 10 to the negative 6th. Remember, this is true because reaction number 3, the one we're working on right now, happened at the same temperature as reaction number 1. So if you look back at your notes, reaction 1 happens at 100 Kelvin. It's the same reaction, so the KEQ is the same. So from here, you might be looking at this problem and realizing, oh goodness, we're going to end up with the quadratic. So you could simplify this. You could take this and expand it so that you know that 1.15 times 10 to the negative 6th equals x squared, all of this over 4.0 minus 4x minus 4x plus 4x squared. You could make this eventually into negative 8x. And then, since this is all in the denominator, we would want to move this over to the numerator side on the other side of the reaction, which would be, if you did this math, 4.6 times 10 to the negative 6th minus 9.2 times 10 to the negative 6th x plus 4.6 times 10 to the negative 6th x squared equaling x squared. And you could subtract this x squared from this x squared so that you have all of this equal to 0, and you could use the quadratic equation. However, in our case, we have a shortcut. If KEQ is less than, the change in x is going to be so small that it's not going to make a difference on the initial concentration. Or I should say, it won't make a significant difference. So if KEQ is super tiny, and in this case it is, look, it is smaller than 1 times 10 to the negative 5th. Ignore x in change of reactant. So, in this case, all of this math that we're doing right here, I'm not asking you to do that. So the change in x again, this is the one that is too small. So we are just going to use 1.15 times 10 to the negative 6th equals x squared, all of that divided by 2. That is a much easier problem for us to solve and not worth all of the extra energy that would go into solving this quadratic equation. So just multiply both sides by 2. So now you have x squared equals 2.30 times 10 to the negative 6th. So from here, the math is pretty solvable. Take the square root. You get x was 1.5165. So if you use, if we use significant figures, we have to round that number. So 1.52 moles. So this is x. We use x to go back to this equation. So at equilibrium, remember, we just assumed that the change in x was negligible because our KEQ is so small. So at equilibrium, the concentration of A is 2 moles. B is a solid, so we don't include it in our calculation. Oh, sorry, this is 1.52 times 10 to the negative 3rd moles. So in C and D, now we know that x was 1.52 times 10 to the negative 3rd. So the concentration of C and D is 1.52 times 10 to the negative 3rd moles. So there you go. That's how you use the KEQ expression. And so KEQ, remember, is the products divided by the reactants. And you have to take each product, take it to the exponent, take each reactant, take it to the exponent of its coefficient. If we have these shortcuts, so if KEQ is less than 1 times 10 to the negative 5th, the change in reactants is insignificant. That's a big help. It will help you avoid an incredible amount of math just to get a tiny, tiny change. And from there, we use the equilibrium concentrations to determine the KEQ value. So that's it. If you need help, you can come see me during office hours. We'll talk about this in class tomorrow. So on Thursday, March 26th, class will be doing these KEQ problems in class. All right, great. Let me know if you have questions.